Como in the late 18th century was hardly the place one would expect to witness a scientific development so dramatic as to transform the study of electricity from the periphery to the very center of science. 200 years earlier, northern Italy had been the home and the vanguard of the emerging natural philosophy. But after Galileo, the new science languished and spread and flourished elsewhere. But now again, for a brief span, two Italian professors, Luigi Galvani, professor of anatomy at the time-honored Bologna, and Alessandro Volta at Como and Pavia, were to occupy the center stage in a remarkable episode in the history of the electrical science, whose climax in 1800 was the discovery of a new source of electricity and its practical realization, the Voltaic pile. We shall not attempt to explain these dramatic events, but rather to picture the stage on which they were set. But first, we must go back to an earlier age, to William Gilbert, physician in the court of Queen Elizabeth I, who, in his lifelong study of magnetism and electricity, first demonstrated the power of the new mode of acquiring knowledge, by experiment, by the study of nature, with probing instruments and skilled hands, with a vigilant eye and an open mind. With him, electricity begins to move, albeit quietly and slowly, into our civilization. In the century or so that followed, natural science took root and flourished, but electricity was still in its infancy. The new mathematical natural philosophy had little direct influence on the early electrical art, which was yet to become a science. For in contrast to the new natural philosophy, which commanded the attention of learned scholars, geometers, and philosophers, the manifestations of electricity were explored for the most part by curious amateurs. Its mysteries and magic were as much a source of entertainment as of enlightenment. They were displayed as often to titillate crowned heads as to stimulate learned ones. Even for those who, over the years, labored to enlarge and order the knowledge of these strange new phenomena, for example, the Honorable Robert Boyle, the Burgermeister von Guericke, Apothecary Sir William Watson, Professor Peter van Musschenbroek, and the Abbé Jean-Antoine Nollet, even for the great pioneers of electricity in the mid-18th century, Benjamin Franklin and Henry Cavendish, the study of electricity was but a sideline. The new science had yet to claim a scholar wholly devoted to its study. Alessandro Volta was heir both to the fledgling electrical science and the established Newtonian natural philosophy. For although in Italy of his time science was hardly lively, the scholarly tradition was certainly not dead. At the ancient universities there were distinguished teachers, Beccaria for example, from whom young Volta could learn much about the development of science elsewhere. And his earliest essays reflect this tradition of lettered scholarship. But it is not so much learned scholarship as experiment that has become Volta's most persistent, demanding, most inspiring and rewarding teacher. For Volta was, first and foremost, an experimental philosopher, a master of the experimental art in the tradition of William Gilbert. And he is the first philosopher-scholar who will devote his whole life to the study of electricity. So whilst elsewhere in Europe, scholars and philosophers were perhaps preoccupied with other more imposing or weighty matters, elaboration of the new edifice of mathematical philosophy and its implications, or influenced by it the philosophical study of man, his manners, his morals, his institutions, or with the impatient and violent translation of social theory into political practice. Volta, in his modest laboratory in Como, was assiduously and single-mindedly mastering every detail of electrical science. So when, in 1791, Volta is to learn of the sensational discoveries of his colleague Galvani, he is fully prepared, engrossed, undistracted, and superbly equipped to exploit their implications. His genius can find its fullest expression. In 1775, Volta announces his first major discovery in a letter from Como to Joseph Priestley. 'Tis the electrophorus, or electrophoro perpetuo, a machine for drawing off electrical charge indefinitely from that infinite reservoir, the Earth. Its construction is simplicity itself. A flat cake of some electric per se, that is an insulator such as sulfur, wax or resin, lies on a conducting surface or metal base plate, which is electrically in contact with the Earth. We charge the cake once, simply by rubbing with a dry hand. On this charged cake, we place a metal disc fitted with an insulated glass handle. With one hand, the top plate and the base are momentarily connected, so allowing electricity to flow, although the charge on the cake itself need not be disturbed. Now we remove the top plate, and it is indeed electrically charged. Electricity has been drawn to it or repelled from it by the fixed charge on the cake. If, as Volta interprets, this charge has come not from the cake itself, but through my hand, from the Earth, then it should be possible to repeat the process ad infinitum. In principle, we need never rub the cake again, and this indeed appears to be the case. And to confirm this interpretation, we repeat the process, but without making the brief connection through my hand. If the charge of the plate were due simply to contact with the cake, this should make no difference. But in fact, there is now no significant charge on the plate. To emphasize its power, he demonstrates how to employ it to amass a really large charge. For this, he uses a large Leyden jar or condenser of capacity sufficient that each time the charged electrophorus plate is brought up, practically all electricity is discharged. So the charge in the Leyden jar mounts to a substantial level. Witness the fat spark when we discharge it. For Volta, as so often in scientific discovery, a first interest, a first success, has a profound influence and a lasting imprint. We shall hear the electrophorus theme echoed time and again in his later work, and never far away is his vision, the idea or ideal of a perpetuum mobile of electricity. The electrophorus was Volta's first major achievement. It brought his work to the attention of the leading European electricians. For several years now, Volta engages in many electrical and chemical investigations in vogue at that time. Discharging gases, electricity in the atmosphere, electrification in evaporation and in chemical processes. In 1781, now professor of Pavia, Volta displays his real flair again. And again, it is the discovery and development of a new technique. A method of rendering very sensible the weakest natural or artificial electricity. Here is a demonstration of it. Weak means electricity of very low tension, and for this we used a very weakly charged Leyden jar, too weak to manifest its electrical charge directly. We look for this by applying the jar to this upper plate resting on a similar grounded plate, but insulated from it by an intervening thin layer of non-conducting material, here shellac. We now separate the two plates, and the charge acquired from the Leyden jar by the upper plate becomes sensible. The two plates, when together, form a condenser, but when separated, the capacity of the upper insulated plate alone is much smaller. Volta's new technique is to apply the weak electricity, which is being examined, while the capacity is large, then to reduce the capacity by separating the plates. The tension rises and the electricity becomes sensible, that is to say, detectable. If we simply apply the weak electricity to the plate when it is separated and its capacity small, we get no magnifying effect and the electricity is insensible. Volta had arrived at this invention only after a long study of a perplexing paradox, the observation that a metal object can often retain some electricity for a longer time when in close proximity to some poorly insulating material than when well separated from all conductors. He surmises, finally, that this is because the metal plate has a much greater capacity when it lies in a proper plane, and this more than compensates for a poorer insulation. This new technique Volta makes more convenient by combining into a single instrument the separable condenser and an electroscope. The combination he calls an apparecchio ingranditore, a condensing or microelectrometer. For convenience, it is now the upper plate which is grounded by my finger. Again, we apply the weakly charged Leyden jar now to the lower plate, separate, and the electrification indeed becomes quite sensible. Volta has now been experimenting with electricity for 15 or 20 years. He is master of the art, one of a handful of experienced electricians in Europe with whom he corresponds. In 1782, he embarks on a grand tour of Western Europe and meets many of the leading scientists of his day. 1784, he is traveling again, now in Bohemia, Saxony, and Prussia. By 1791, he is a Fellow of the Royal Society, a corresponding member of the French Academy. His scientific works have been translated into English by Cavallo. He has explored electricity in innumerable guises, natural and artificial. He has displayed an outstanding ability to unravel its obscure manifestations, and he has the prophetic assurance that his new sensitive techniques will be of the greatest advantage for the science of electricity. But this insight, this skill and ingenuity notwithstanding, the fruits of his labor are hardly sensational. It is as if Volta awaits a real challenge to his powers. In 1791, the challenge comes, and Volta moves swiftly to meet it. There is no doubt about the immediate stimulus that started Volta on the decade of intensive experimentation whose climax was the invention of the pile. It was the receipt from his colleague Galvani of a modest account, but based on many years of patient work, of some remarkable observations with electricity and dissected frogs. Galvani had written how he had dissected a frog and prepared it, placed it on a table on which there was an electrical machine, whilst I set about doing certain other things. One of my assistants touched lightly by chance, with the point of the scalpel, on the internal crural nerve of the frog. Suddenly, all the muscles of his limbs were seen to be so contracted as if they had fallen into tonic convulsions. Another of my assistants seemed to notice that this happened only when a spark came from the machine, which was no small distance away. This association, despite the absence of direct electrical contact, leads Galvani to inquire whether perhaps the same physiological effects could be produced by atmospheric electricity. Surprisingly, he found that frogs suitably prepared and fastened by brass hooks in the spinal marrow to the iron lattice around a hanging garden in my house exhibited convulsions not only during thunderstorms, but sometimes even when the sky was serene. Galvani explained, "For many days I watched the frogs, but could detect no motion. Weary of waiting in vain, I pressed the brass hooks against the iron lattice. I observed convulsions, but they did not seem to bear any relation to the electrical state of the atmosphere. I came very near to adopting a theory that the contractions were due to atmospheric electricity, which had slowly accumulated and was then suddenly discharged. But," he goes on, "I took the animal indoors, placed it on an iron plate, and when I pressed the hook, which had been fixed in the spinal marrow, against the plate, behold, the same spasmic contraction. I tried other metals at different hours, on various days, always with the same result, except the contractions were more violent with some metals than others." Animal electricity, that is, the generation of electricity by some live organisms, was well known to Galvani and contemporary anatomists. It is no surprise, then, to find Galvani, after rejecting external electricity as the cause of frog convulsions, adopting a theory of internally generated animal electricity discharged via external conductors. This whole realm of animals, dissections, nerves, and muscles was for Volta a wholly unfamiliar one. But his immediate reaction as an experimenter is to examine and reproduce the strange phenomena under his own hand and eye. But in contrast to Galvani, Volta's experience is in physics and chemistry. How natural then for him to seek an explanation, after he has verified the phenomena, in terms of some physical cause, some external source of electricity. Consciously or not, he was predisposed to this view from the outset. As an experimental philosopher, it is to experiment that he now turns to guide and sustain his suspicions. Not one or two experiments, but dozens, hundreds, even thousands. In a favorite phrase, par mille expériences, and with seemingly remorseless logic, he confirms his view. By a bold continuation and extension of Galvani's own experiments, he stands the Galvani hypothesis on its head, or perhaps puts it back on its feet. The prepared frog does not generate electricity, but responds to it, and a most sensitive responder it is. Had not Galvani himself earlier remarked just this? There must, Volta surmises, be a strange new source of electricity in Galvani's bimetallic arcs. This Volta confirms by showing that any other plentiful source of weak electricity, for example the weakly charged Leyden, can, if only it is suitably applied to the nerve itself, elicit the same convulsive response. And this for all animals, whole or part, dead or alive, wherever there is a voluntary nerve muscle system. He tests his hypothesis not only on the frog, but with every conceivable species he can lay a hand or scalpel on. Birds, fishes, insects, reptiles, hot and cold-blooded, bipeds and quadrupeds, vertebrate and invertebrate, snails, worms, flies, butterflies, leeches, lizards, salamanders, scarabs, oysters, crayfish, and so on. And finally on his own person, his hands, his mouth, his tongue, and his eyes. This is one type of experiment he makes. Take a pair of metal strips of different metals, of course, here zinc and copper. Place their ends close together on the tip of the tongue. One can feel them, but one tastes nothing in particular. Now bring the ends of the strips into contact. Immediately, or so it seems, there's a salty sensation on the tongue. Another way of examining this bimetallic effect is to place one metal strip very carefully in the corner of the eye, and a strip of different metal in the moist hand or mouth. On closing the bimetallic circuit, there's a sensation of a flash of light. From these mille expériences emerges Volta's basic principle. A metal, when in contact with another, does not act simply as a passive conductor, but as un véritable moteur d'électricité. Metals differ in their motive powers, so that in the contact of dissimilar metals, the equilibrium is disturbed. Electric fluid is caused to flow, gently but in large quantities, in the direction of the stronger power. And it will continue to do so as long as there is a continuous closed circuit to permit circulation. But this path cannot be completed by a metal class 1 conductor, for then there would be several bimetallic contacts acting in conflicting directions and in toto cancelling. Thus, if we had a closed loop of two metals only, say silver and zinc, there must be a silver-zinc contact in one place and an opposing zinc-silver in another. A net effect is zero. With three or even more metals, the combined effect on Volta's hypothesis would still be zero. But if the circuit is completed by means of a wet class 2 conductor, which on the hypothesis generates only very weak power on contact, one can bypass this difficulty. A continuous circulation is now possible. This then is the basic voltaic circuit element. A motor comprising two dissimilar metals, class 1 conductors, and the circuit completed by a passive class 2 conductor. All metals are now tested and measured, and a hierarchy of their powers drawn up. The greater the separation in this hierarchy, the greater the bimetallic power exhibited in the basic circuit, which can be tested by the frog or any other animal response. The animal provides both the harmless wet class 2 conductor and the detecting instrument. In Volta's theory, the ordering should be the same whatever the physiological response, as indeed he finds. This basic theme is explored in numerous variations and elaborations. All point to Volta's new contact electricity as the source of Galvani's frog convulsions. The frail arguments of Galvani and his followers cannot sustain Volta's massive experimental evidence and logic. His views prevail. The highest award of the time, the Copley Medal of the Royal Society of London, is conferred upon him. He has triumphed scientifically. He has explained the mystery of galvanism. But if this is the end of one long road, it is also the beginning of a new journey. Galvanism, with its frogs, nerves and muscles, Volta now leaves behind him. For if these are, as he indeed sees them, just electrically passive Class II conductors, and incidentally convenient detectors, it must be possible to demonstrate the new electricity unequivocally without their use. But how can one dispense with a prepared frog, which is, after all, the most sensitive available detector, the very one which made the discovery of the new contact electricity possible? What other instrument can one use? It is now that Volta's superb mastery of the electrical art displays its full power. Had he not, 10 years ago, invented his microelectrometer for the examination of just such weak electricity as this? Let us see how he utilizes it. The two brass plates comprise the condenser of the microelectrometer. First, we must carefully ensure that it is totally discharged, no trivial task. We take two strips of metal, one copper, the other zinc, each in contact with a bit of wet rag, a Class II conductor, all that remains of the prepared frog. We bring the zinc into contact with the upper plate and the copper into contact with the lower, thus charging the condenser. After removing the strips, we separate the plates and we see, magnified as it were, distinct evidence of electrification. We must test with a rubbed glass rod the sign of this electricity, and then we should check, as Volta invariably does with meticulous thoroughness, that reversing the roles of copper and zinc would reverse the sign. There is not here a truly closed voltaic circuit, nor do the copper and zinc form a direct bimetallic contact. Volta interprets this experiment in terms of two bimetallic contacts, a copper brass and a brass zinc, whose combined motive powers disturb the electrical equilibrium. The passive wet rag allows electricity to pass from one brass plate to the other, and it is this transfer of electricity which we observe. It is 1797, 6 or 7 years since Volta embarked on his exploration of galvanism, and he is now near his final destination. He has managed to demonstrate his contact electricity without using any animals. But the effects are weak and the function of the wet conductor controversial. It is the chemists now, rather than the anatomists, who question his theory and whom he must convince with a clear-cut, clean, dry physical experiment. This would be the final irresistible proof. Why not, Volta asks himself, use the two contacting metals as a sort of condenser in themselves, like the metal and insulator slab in his old electrophorus? And this already enhanced electrification could be further augmented by repeated charging, as in the electrophorus Leyden jar technique. And finally, the effect magnified and made fully visible by his own microelectrometer. For this, the metals must be in close contact over a large area, and clean and smooth and flat. Here are two such plates, one copper and one zinc, and with them we perform the experiment which is Volta's masterpiece. First, the check that the condensing electroscope is thoroughly discharged. Bring the two metals into close contact. Now separate them sharply and squarely. If Volta is correct, electricity has flowed from one to the other. Both copper and zinc are electrified in opposite senses. The charge on the copper plate, held by its insulated handle, is now deposited on the insulated plate of the condensing electroscope. And we can go back and repeat the process 5, 10, 15, 50, or even 100 times. About 25 should suffice. We open the condensing electroscope, there is no doubt about the result. Who can now challenge Volta's claim to have discovered a new sort of electricity, and his right to name his own discovery, bimetallic or contact electricity? For Volta's contact electricity, the more contacts, the more electricity, up to a point. We can check this. Replace the condenser plate on the electrometer and go back for more charge, 10 more taps. Open the condenser, and indeed we have more. We can go back for still more. In some cases, with only slightly dissimilar metals, Volta continued for hundreds of tappings. Always, of course, there's the check for the sign of the electricity and its reversal when the metals are interchanged. For Volta, there is much more. The hierarchy of the metals must be checked by this new technique, and his theory must be tested by altering in this way and that the precise mode of making contact and separation. The clackety-clack we heard a moment ago is not incidental. He must make the effects come and go at his command. All spurious electrification must be eliminated, all doubt removed. One task remains. Rather than render this weak electricity perceptible by ingenious magnification, augment the phenomena itself. Prove that the new electricity is not only the same in essence as the old electricity of sparks and shocks, but can match it and perhaps exceed it in size and power. With confidence in his understanding, this task for Volta is unbelievably simpler. All that is necessary, in place of a single bimetallic element, is a multiple array of the same, connected in proper order, each to the preceding one by a harmless, wet class 2 conductor. Literally, one can pile one element on top of the other, almost ad infinitum. Here, in Volta's own words, are the simple instructions. 30, 40, 60 or more pieces of copper, or better, silver, applied each to a piece of tin, or zinc, which is better, and as many strata of water or any other liquid such as salt water, ley, etc., or pieces of pasteboard, skin, etc., well soaked in these liquids. Such strata interposed between every pair or combination of the two different metals in an alternate series, and always the same order of these three kinds of conductors, are all that is necessary to produce my new instrument. Having all the pieces ready in good state, the metallic discs very clean and dry, and the non-metallic ones well moistened, I have nothing to do but to arrange them, a matter exceedingly simple and easy. The apparatus is, as Volta emphasizes, susceptible of many variations on a large or small scale. His famous crown of cups, in which the moist discs are replaced by separate cups of liquid, and the metal discs by strips, is one such variation. With this pile of some 200 copper zinc elements, we can make the electroscope move directly, the hallmark of genuine electricity. And if we use it in conjunction with the condensing electroscope, the magnified effect is sufficient to see even on the crude pithball detector. For Volta, the pile represents his contact electricity fortissimo. It is the summer of 1800, more than 30 years since Volta started his electrical researches. This final success, even after all his earliest successes, is for Volta himself almost unbelievable. He cannot contain his excitement. He must convey the news to the world. And in his letter to Sir Joseph Banks, President of the Royal Society, none of his elation is concealed. His new instrument, he emphasizes, is constructed according to the principles of electricity discovered by me some years ago, and which my successive experiments have so well confirmed. For Volta, the discovery of the new electricity rests firmly on his mastery of the old. And does it really matter now if he cannot convince the skeptical with his extraordinary theory of the new electricity? Anyway, he retorts, who really understands how the old electricity is made? Practice speaks louder than theory. The pile works. For Volta, the pile is the climax and the end of his scientific career. For science, it is the opening of a new epoch. Electricity can now be produced in a copious, steady stream, in vivid contrast to the meager flow from the old ordinary machines. The tension may not be so great, but this is more than compensated by the quantity. Moreover, the pile is so simple, anyone can build one. Voltaic piles or arrays are speedily assembled in all the leading scientific centres. Within days of Volta's letter reaching London, Nicholson and Carlisle, using the new instrument, demonstrate the decomposition of water into its constituents, hydrogen and oxygen, and thereby confirming what Cavendish and Lavoisier had shown in reverse some 25 years earlier. Voltaic arrays grow larger and grander. Within a few years, the renowned chemist Humphrey Davy exploits his power to isolate remarkable new chemical elements, metallic sodium and potassium, and to demonstrate the brilliant light of the electric arc. 20 years later, Hans Christian Ørsted discovers the magnetic properties of the Voltaic galvanic circuit, and the 19th century era of electrical science is in full swing. Volta had opened the door to this momentous development. Volta himself took little part in this great exploitation of the pile, whose practical value was incontrovertible. Not so Volta's theory of the pile, his basic contact electricity, which was suspect from the outset and was the subject of controversy for many decades. But after briefly, though staunchly defending his own views, he withdrew from this debate also. For Volta, now 55 years old, soon retires from active science. Prizes and honors are heaped upon him. Acclaimed, bemedaled, elevated to the rank of senator and later count, by order of no less an admirer than Napoleon himself, he seems not indisposed to enjoy the fruits of success in tranquil, dignified domesticity. The dazzling success of the pile helped to eclipse not only the deficiencies of Volta's own theory in his own lifetime, but also his place in history as the discoverer of true contact electricity. In Volta's own theory, the pile and contact electricity were manifestations of one and the same principle, a sort of perpetual mobile of electricity. Volta's archaic theories are now not only discarded but forgotten. But wisdom is to be judged by its children. For Volta, the experimental philosopher, theory was a guide, subordinate to his experiments. Volta's theories are best judged by the great discoveries they helped him reach and the electrical science these in turn begat. It is not unfitting then that 80 years later the word volt is adopted as the unit of electrical tension or potential difference, and Volta's name becomes immortalized in our language.